Okay, welcome everyone. We've got the 22nd. It's Wednesday. We're going to continue this fascinating discussion of principal axes. And it's really interesting how we're going to see some behavior here from even simple systems such as a rigid object with no applied torques, no forces applied, no torques applied. This is called the free rigid. There's some fascinating physics here that we're going to investigate. And without further ado, let's watch a brief video clip coming from the International Space Station. Okay, so astronauts on board the International Space Station prepared this nice video clip because in a zero-G environment, you can do some wonderful stuff. So I'm going to click here. Let's see. So at this point, let me move the chat when I think it's probably not a problem for you, but for me, it's a problem. Okay, so what we have here, if you're aboard the space station, there's something called a T-handle, and you see the title here, Dancing T-handle. There's some remarkable behavior. And this is a rigid object with no torques. There are no external torques acting upon this object. So it's remarkable. It appears to, let's play again. Okay, once again, it's a rigid object with no external torques. And there's this very fascinating behavior. It appears to kind of flip over every so often. Okay, now remember, this problem is of fundamental interest to us because here we go. Once again, this is in slow motion. And we'll talk about how, in fact, the slow motion is completely valid. There's no way to look at this video until it's slow motion. It's also a correct solution for the equations of motion if you slow down the video. Okay, so that was fascinating. Let's go with the stop share. Okay, so we're back here to our chalkboard. Once again, we're talking about a rigid object with no forces and no torques acting upon it. In some sense, this is one of the simplest problems you could study. The only thing simpler is a point particle. We've already solved that, right? A point particle would just move in a straight line with constant velocity if there are no forces acting on it. So a rigid object with no forces and torques acting on it is surprisingly complicated, okay? And I mentioned this as a motivational remark. Of course, we're going to analyze the motion you just saw, the dancing T-handle. And I should just remind you, a T-handle, if you're an astronaut aboard a spaceship, you probably will have a T-handle with you. What is this? Well, it's a handle that you can hold on to, and there's a threaded rod coming out of it, so you can thread it into any of the many holes that are available on the wall. And this gives you a handle to hang on to as you're working on something around the ship. It's just a little annoying when you start to drift away. You're trying to do something and you drift away. Well, the T-handle, as we've been doing our ancestors millions of years ago, right? That's why we have hands, so we can grasp onto things, tree branches or T-handles. So yeah, the T-handle is something you have with you. And then they realized when they unscrewed it from the socket in the wall, of course, the cool way to do it is give it a flip with two fingers. In fact, we should probably just watch the video again. Once again, I'll click share and we'll go for this one. Yep. Play again. So there it is. You see the cool trick, right? The T-handle was threaded into this hole, and it's small, but you can read it. It says T-handle there. In case you're wondering what the threads are for that one, that's the proper thread for your T-handle. Again, it's a handle that you hold on to. I'm showing with the mouse pointer. Then we have this attachment here with a threaded rod. It's kind of blurred right now because of the motion. The astronaut just illustrated the cool way to unscrew it from the wall is give it a flip like this. And there you go. And now we have talked about stable and unstable. By the way, that was a nice shot of the threads. Here we go. Once again, I'm going to pause it. Yeah. So this is a threaded rod, just as you have in the laboratory. Any sort of machine screw has threads there, and you screw it into the hole in the wall. Okay. We've talked about stable and unstable equilibrium. For example, for the pendulum, when the pendulum hangs straight down, that's a stable equilibrium, right? You give it a little bump, it stays nearby. It oscillates about the equilibrium. That's in contrast if you build a pendulum with a rigid rod rather than a string. There's another equilibrium when the pendulum is pointing straight up. That's an equilibrium. That's a solution to the equations of motion if it's perfectly balanced, but it's not stable. The tiniest little bump will grow exponentially with the initial growth for small excursions, right? We can do a small angle approximation. The initial growth is exponential growth. So in that sense, we've talked about stable and unstable equilibria. This is a different story, and we're preparing the mathematical framework now. We're launching into this discussion with the principal axes. How do you talk about stability and lack of stability when you're talking about the motion of an axis of rotation? Okay, again, the axis of rotation is not a physical object. It is a construct of our minds, the instantaneous axis of rotation. So how do you talk about the stability or lack of stability of an axis of rotation? Well, that's what we're going to set up. There's a right way and a wrong way to do this. Actually, pretty much one right way, many wrong ways. Okay, so let's go ahead and return to our chalkboard. Stop. Yep, here we are. So we're going to set up the framework now, and the crucial tools now, we must be cognizant of these so-called principal axes. Okay, this was the formula here. If you find, okay, the logic goes like this. If you can find an omega vector with the property that you rotate the rigid object as per this omega vector, that means the omega vector, of course, it tells you about an axis of rotation, and the rate of rotation about that axis is not critical to us right now. You see, you could double this omega vector and you would still have a solution of this form. The angular momentum would be parallel to the omega vector. So the crucial thing here is the direction. And that's why we use the word axis. Okay, so as you know, it's true quite generally. Okay, so this is true in general. Okay, and the first equation, this is a very special state of affairs. Okay, it's a very special case that the angular momentum points in the same direction as the omega vector. Let's take a moment to gain a little bit of familiarity. This is somewhat mysterious, right? So let's talk about this. And here we go with this item. Oops, I did bump the document camera, but the tripod is pretty decent. This is actually a special tripod for astronomy, so it's very stable and strong. Okay, so here's a rigid object. Okay, and later today, the illustration with the dancing T-handles, you can also, a very popular way to demonstrate that at home is with a tennis racket. Now this is a table tennis paddle, but in terms of the physics, we'll talk about how you can demonstrate that dancing T-handle remarkable behavior. You can demonstrate it with a tennis racket. If you don't have a tennis racket or a table tennis paddle, you can do it with a textbook and a rubber band. You take a textbook, you wrap a rubber band around it so the book doesn't open up. You don't want the pages getting messed up, etc. So you can certainly demonstrate this fascinating behavior in your home laboratory. You can do it today after lecture. You could even do it during lecture. But we'd kind of like you to stay tuned here for lecture and then experiment after lecture. Let's talk about this object here, okay? So first of all, suppose we have an axis of rotation. What we're going to see, if you have an axis of rotation, and I'm indicating with the pen here, I should probably scoot this up some more. Okay, here we go. Suppose this is your axis of rotation. We're going to think about the total angular momentum of that object about its center of mass. And I think you can see based on your intuition that in this case, the angular momentum will be parallel to the axis of rotation. We'll talk about that in more detail. Really what you need to do is subdivide this rigid body into differential installments. For each one, compute the contribution to the total angular momentum. And we'll talk about why that should point in the same direction as this axis of rotation. But now let's look at a different example. Suppose, okay, we take the same rigid object, and now again, the pen indicates the axis of rotation. Notice the axis of rotation goes through the center of the object. We're going to see for this example, the angular momentum vector is not parallel to the axis of rotation. All right, so this is kind of the basic playing field that we have here for this analysis. For any rigid object, you can contemplate any sort of axis of rotation through its center of mass. And for most of them, it will be true that L is not parallel to omega. Okay, quite generally, L is not parallel to omega. It's a very special case. For example, this axis of rotation here, you get L parallel to omega. Okay, again, let's assume the center of mass is right there in the center of this housing for simplicity. And again, here's another case. If the pen indicates an axis of rotation, then in this case, again, let's assume the center of mass is in the center. Then you have L parallel to omega, and also this one here. So this is, we've identified three principal axes. Okay, so let's talk about this. Why would it be true that in some cases you have an angular momentum vector that is not parallel to omega? Okay, let's draw a picture. Okay, so here's an object. Let's suppose this object is made out of styrofoam, and then somehow we have caused a concentration of mass over here. Maybe you drilled a hole in there and filled in some very dense material, and another concentration of mass over here. Okay, so this shading indicates regions where the density is much higher. Okay, the center of mass is here. All right, I see I've started drawing small again. I'll make an effort to draw things bigger, but that's a pretty simple diagram. We have the styrofoam there is just to help for clarity to think of a single rigid object, okay? Of course, the density can vary, and this is a rigid object where we have very pronounced high density at this location and very high density here. All right, suppose you force this to rotate about a vertical axis. Okay, and notice I said force. This thing will not just spin by itself about this axis. You must have some sort of laboratory equipment with an axis of rotation and some bearings that are securely mounted to your workbench, etc. So we're going to force it to spin about this axis of rotation. Okay, so again, if the omega vector points straight up, let's think about the angular momentum. What can we say about the angular momentum? Well, let's consider this extreme case where the styrofoam is essentially massless and we have two massive objects like so. Well, at the instant we've drawn here, okay, where this massive object is to the right, it will be traveling straight down into the paper. So the velocity of this massive object is straight down into the paper. The r vector, okay, that's the r vector. So what's r cross p? R points there to the upper right, and the p vector is straight down. So r cross p is like so. So the contribution to the angular momentum okay, so we've analyzed that particle. Turns out this particle has a very similar contribution. Because of the rotation in the right-hand rule, the velocity vector for this massive contribution is straight out of the paper, perpendicular to the paper, coming straight out. And here, for this one, r vector Here's our r vector. So once again, r cross p points that way, because this r vector is -1, that r vector, -1 times that one. And this velocity vector is -1 times that velocity vector. So it's no surprise the angular momentum vector points like so. Okay, so this is a nice example. Again, it requires an apparatus to, if you would like this to be a steady state, ongoing state of affairs, that this is the axis of rotation, then you would need some laboratory equipment. If you don't have the laboratory equipment, you're welcome to launch it with this as the initial axis of rotation. The axis of rotation will change in a complicated manner that we're going to investigate. But for that first instant, you can arrange for this to be the axis of rotation. And at that first instant, this is your angular momentum vector. So it's a nice example of how the angular momentum vector in general is not parallel to the angular velocity. So it's a very special case. So for this object, if we spin it about this axis, then yes, the angular momentum vector is parallel to omega. And furthermore, if we spin it about this axis, I have to be very careful. I have to hold it perpendicular to that. Yep. Once again, so yeah, you see there are special, the takeaway message here, there are special values for this vector omega where the resulting angular momentum of the rigid object is parallel to omega, okay? And those special directions are called the principal axes. So that, notice the word here, axis. We don't care how long or short this omega vector is, right? Because this discussion is immune to any sort of multiples of omega. The direction is the key, right? There are special directions. And in the language of linear algebra, we're talking about a one-dimensional vector space, right? That's the right way to formulate this. There's a one-dimensional vector space. If you do find such an omega, then the span of that omega is a one-dimensional vector space in a three-dimensional world, right? It's a one-dimensional subspace, and these are the so-called eigenspaces. And there are special cases where you have two-dimensional eigenspaces. We'll talk about that. Those are kind of special cases. But a generic object, remember we talked about going for a hike up in the hills behind the Berkeley campus, you find a boulder with some funny shape, a completely random generic object. It's remarkable. It will have three principal axes that are perfectly orthogonal to each other. That's one of the first things we'll prove. Okay, so quite generally, a rigid object has these mutually orthogonal axes. In special cases like a sphere, if you have a perfectly spherical distribution of mass, then every direction is a principal direction. And you can arbitrarily choose three perpendicular axes to be the principal ones, but that's again a special degeneracy, right? When two eigenvalues are equal, you have a degeneracy. Yeah, so that's kind of the big picture we're working towards. And again, we'll talk about how you can demonstrate this fascinating behavior at home. The result that we're going to prove here, and this is such a surprising result. Some people, when you tell them this result, some people, I've talked to people with degrees in physics who just simply refuse to believe this result, that for a generic rigid object with three different principal axes, so three different moments of inertia, two of them are stable and one is unstable. Okay, and so for the tennis racket, yeah, this thing is too big for the document camera, but for a tennis racket, this axis is stable. This is well known to tennis players. You're standing there waiting for your opponent to serve. You typically spin the racket in your hand. And if you let go, it will continue to spin about that axis. It might fall to the ground, but that's a separate issue. That's the center of mass motion. This is a stable axis. And hopefully someday you can do this on the space station. Take a tennis racket, spin it about this axis or a nearby axis. It might wobble a bit, but it will continue to rotate. The other thing you can do with a tennis paddle is you can, I should say, table tennis paddle or tennis racket. It will spin stably about an axis. Let's say the center of mass is right here, okay? Then this axis, again, is stable. And again, this is well known to tennis players. You can flip the racket, you throw it in the air, and then again, you catch it by the same handle. In an emergency catch it, just grab onto whatever part you can. You don't want to drop it. Not good for it. But yeah, again, this axis of rotation is stable. Now, what's remarkable, and this is fun to play with, there's one more axis that we should talk about. Again, assume the center of mass is here. It turns out this axis is unstable. And this is a fun challenge. You want to, if you want to experiment, do this over a soft surface such as a deep carpet or some couch, something like that, something soft. Because your goal is to throw the paddle into the air and have it rotate about this, it's a little hard to hold, have it rotate about this axis, okay? So, and it's extraordinarily difficult. The tiniest of errors will grow exponentially. And that's what we saw in the dancing T-handle in that video. We saw essentially the lack of stability of this axis. So I'm rocking it back and forth, but imagine steady rotation about, you see I have two fingers in contact with the paddle. And all I can do, because the document camera is blocking me, I can just rock it a bit. But yeah, you can demonstrate this with a textbook too. If you put a rubber band around a textbook, two of the principal axes are stable and one is unstable. So that's a fascinating result. All right, it's called the intermediate axis theorem. We'll see that the axis with the largest moment of inertia is stable. We'll see that the axis with the smallest moment of inertia is stable, but there are three axes. The one with the intermediate moment of inertia is unstable. Okay, and that's what that demonstration was with the dancing T-handle. So yep, fascinating stuff. Those were some motivational remarks because we're going to have to do a bunch of linear algebra here to really set the stage. All right, so let's appreciate that there's fascinating physics ahead, fascinating applications. All right, so we wrote down the equations last time. Quite generally, the angular momentum vector is gotten from the omega vector by multiplication. Here's this matrix, right? You take the matrix, you multiply the matrix times omega, that gives the angular momentum vector. Now we're looking for special cases where this angular momentum vector is just a number times omega. That is the statement that is parallel to omega. Okay, so we wrote that out last time. Yeah, we had to introduce the 3x3 identity matrix. Okay, so this construction again, this can be a little bit weird if you see this typeset in a book. Notice that's a capital I. If you see this typeset in a book, it's going to be a boldface capital I. This is the numeral 1. The numeral 1 is appropriate as our symbol here for this matrix. The numeral 1 with the double-headed arrow is a matrix. That's the identity matrix, meaning if you multiply this matrix times a vector, you get the same vector, okay? So it's certainly appropriate to call this thing the identity matrix and use the numeral 1, that thing right there. But notice if you typeset in the book, these two things, they're both boldface, but it's definitely a confusing challenge to typeset that. So it's actually very nice when we write it by hand. Notice I've made an extra effort to indicate that's a capital I. I'll even improve my capital I. Yep, it's a capital I. Double-headed arrow. Here's that, it's a scalar, right? A single number, this lambda. And here's a quick question. What are the dimensions of lambda? Well, you know the dimensions of angular momentum, right? It's r cross p, and omega has dimensions in inverse seconds. So once again, moments of inertia, they're kilograms times square meters. And this eigenvalue here must have the same units. In terms of the mathematical setting, it's a much different object, right? That moment of inertia tensor is a 3x3 matrix, and this is a single number, but they have the same units, kilogram meters squared. Okay, so what we saw is that this object, this matrix, which is in parentheses here, it's computed one multiplication, scalar times matrix, and then one matrix subtraction. The resulting object is a matrix. So this thing inside parentheses here is a matrix. The reason we have parentheses there is we're going to multiply that matrix times omega. We get a 0, right? So this statement here is just taking these two statements and putting them together. okay? Rearranging. And now you know from your course in linear algebra, if you have a 3 by 3 matrix, multiplying a non-zero vector, if you get a 0, then the determinant of this matrix must be 0. So the DET, that's the determinant of this matrix, okay? And it's if and only if, right? The logic goes both ways. If the determinant of this matrix is 0, then there must exist at least one omega vector which vanishes, the so-called null vector, right? If the determinant is 0, then you must be able to find a linear combination of the rows or columns that gives you a 0. It's guaranteed by linear algebra. Conversely, if you have a solution, then you can argue the determinant is 0. Okay, so it's if and only if. So, and we pointed out last time, this equation now is it's an algebraic equation. We have a cubic polynomial. Cubic All right, so we got a cubic polynomial in lambda. All right. So far so good. What we can do then is for various mass distributions, you can compute the inertia tensor and compute the principal axes. But before we get bogged down in the algebra, let's try to understand this fascinating behavior. We saw the astronaut showing us that for the dancing T-handle, let's draw a picture of a T-handle. Okay, so examples here. Let's talk about the T-handle. Okay. And you know what happens if you're an astronaut and you lose your T-handle? It means you have to steal somebody else's when they're not watching, right? So here's the situation with a T-handle. Okay, so you have a cylinder, which is the thing that you hold on to, right? That's the handle part. And now perpendicular, you saw this in the video, perpendicular to the handle, you have another cylinder. And for simplicity, let's attach it like so. Right? And actually there's even a threaded rod coming out of here. And that threaded rod threads into the hole in the wall. So you can hang on. Okay, so we'd like to understand this T-handle. Okay, we're in the business of understanding the T-handle. We need to think about the center of mass. We need to think about the principal moments of inertia. Okay, let's talk about another example. So this is the T-handle example. Let's talk about a tennis racket. Okay, we could draw a picture. I think what I'm going to do here for the tennis racket, since I have a picture in the notes, let's talk about this picture, which is available in the notes. And what I'm going to do is I have to do a little origami here because I don't want to cause a PowerPoint overload. So I'm carefully folding this. Yep. You got to take your time when you do origami. Don't rush it. Here we go. So, yeah. Here's a tennis racket. Look at that. We just saved a ton of time. All right, let's talk about the tennis racket, for example, as one of these nice examples. Suppose you have a tennis racket. This, of course, is a perspective view of a tennis racket. All right. Let's say the center of mass is right here. It's labeled with CM, very popular abbreviation. You know, there are three principal axes, okay? And again, this is a perspective view. We have This dashed line is actually a dotted line, kind of this is what you could call the longest axis, right? It's the longest axis because that's what people would talk about when they indicate the region where the mass is present along the axis. So starting from this location here to that location over there, for this particular object, that's the longest physical dimension, the longest length that you're going to measure along the axis. So some people will call this the longest axis. Notice the eigenvalue is actually the smallest. And let's talk about that because we want to start building some experience, want to have some actual intuition for these problems with moments of inertia. Why is this the smallest eigenvalue? Okay, and the short answer, right, again, we want to build intuition. Why is that the smallest eigenvalue? It's because the mass is closest to that axis. Remember, in the spirit of cylindrical coordinates, in cylindrical coordinates, we're often talking about your distance from the z-axis. And in cylindrical coordinates, we call that the rho variable, R-H-O, rho, Greek letter. So in the same spirit, think of this axis, right? And think about how you would compute the moment of inertia about that axis, okay? In your first year physics course, we talked about this. You chop the tennis racket up into little pieces. Every little piece contributes its mass times the square of the distance to the axis. So here's a little piece. You look at the square of the distance. Okay, that's that. What about over here? You see, these are going to be very small contributions because every little differential portion in the handle very close to the axis of rotation. And again, it's differential mass times the square of your distance. So when you add up all those contributions, you see this is the smallest eigenvalue, lambda 3, in this case, the smallest. Now let's understand why this lambda 1 is the largest. And this is true quite generally if you have a rigid object, either if it's planar, and we'll talk about this on the homework, planar, or if it's nearly planar, like this tennis racket, it's not quite planar, it doesn't lie in a plane, but it's pretty close. If you lay the tennis racket down on the tennis court, it's pretty much a flat object laying there on the surface of the court. And so perpendicular to that plane, that's where you have your largest. Okay, so now I'm indicating with the pen, this axis, which is perpendicular kind of to the dominant plane of the racket, again, we're going through the center of mass and we're perpendicular to the plane of the racket. That's where you have the largest lambda. And again, speaking in terms of intuition, we'd like to have large contributions. And when you add up all the differential contributions, differential mass times square of distance to the axis of rotation. So let's look at the handle again. You have a little differential mass here. You must add that differential mass times the square of the distance. The axis is way over here. So you got a huge distance. So therefore, this, what we call lambda 1 in this picture, this is the largest principal value. This is the largest eigenvalue. And when you rotate the racket about an axis perpendicular to the plane of the racket, that's where you get the largest angular momentum for a given angular velocity. Okay. And now perpendicular to both of those is this mysterious intermediate axis. Okay, so these three axes are mutually perpendicular. And this one is intermediate. The eigenvalue is larger than lambda 3. And you can see that because lambda 3, when you think about that lambda 3 axis, the number 3 axis, if you imagine viewing the object along this axis, the mass is fairly close to the axis, so you get a very small moment of inertia, smallest here. This is the largest. The mass is as far away from the axis of rotation as you're going to get it. And this is intermediate. Some of the mass is now closer. So for example, you can pick out a mass here, for example. Think about how far away it is from that axis of rotation. And then you see for lambda 2, you're looking at the distance from this differential mass over to the axis of rotation. That's a lesser distance, a smaller distance. So yeah, this is the intermediate axis. Lambda 2 is greater than this one, that's the smallest, and lambda 2 is less than that one, that's the largest. Okay, and again, I encourage you to do this immediately after lecture. Go to the nearest tennis court if necessary. Actually, it's better just to get a rectangular block such as a textbook and put a rubber band around it. Now you have a rigid object. If it's a rectangular box shape, and if the edges are different lengths, okay, then, yep, so in fact, here's our textbook. Okay, so if you have a solid rectangular object, and we don't have a lot of space here below the document camera, but you see, having taught the course many times, this edge is fairly small, right? This edge is intermediate, this edge here, intermediate. And then you have a very long edge, much too long to put on the document camera, but starting here, going all the way down here. Okay, so 3 different, yeah, you can definitely demonstrate this, but again, that textbook is so heavy, if it lands on a surface, I really wouldn't recommend doing it with that textbook. It puts a lot of stress on the binding every time it hits the ground. So, yep, I'd go with the table tennis paddle and do this either over a carpeted or a sofa or something like that. And now you've got an ideal setup. You don't have to worry about damaging anything. You can demonstrate this fascinating thing. Okay. So the T-handle, let's just make a connection with this one. It'll be a similar discussion, but then we'll understand what's going on in the video. Okay, so the center of mass, well, let's do a very careful construction. First, let's diagram the axis of symmetry of this main cylinder. Okay, now let's be very clear here. This is the axis of symmetry of the handle portion, but not the entire object. Okay, because this object has some mass. So let's say the center of mass, okay, now here's the axis of this little thing. Okay, so this point here, this is the intersection of those 2 special axes. Those are axes of the cylinders. Now the center of mass, let's emphasize this with some dramatic red color. The center of mass is actually here. Okay, so you see we have to be careful. Again, using the black ink, I indicated the axis of symmetry of one of the cylinders, the big one there. That's the handle that you hold on to. And then here's the axis of symmetry of the other cylinder, this smaller cylinder. This one threads into, okay? And there's the intersection of those 2 axes of cylinder, the axes of the 2 cylinders. Okay, obviously that's an important construction, but we need to know the center of mass. Right, we're going to be interested in rotations about the center of mass. In the absence of any forces, you can arrange for the center of mass to be motionless, right? You know from first year physics, center of mass is not going anywhere if you prepare the system with 0 center of mass velocity and there are no forces acting on it. So that's very useful here in these discussions. So now the principal axes, the 3 of them are going to go through the center of mass, okay? And you can see based on this construction, the principal axes will, first of all, I can now use very pronounced dashed lines here for the principal axes. They have to go through the center of mass. Obviously, this one's going to be a principal axis. You can see from symmetry that if you rotate this object about this axis, the angular momentum will be parallel to that axis. Now here's the crucial thing. I'm drawing another axis. You see it's going through the center of mass and it's parallel to the central axis of the large cylinder, okay? And then of course we have perpendicular to both those, and this is perspective view, of course, and there we go, I'm drawing. Okay, so the abbreviation you see quite a bit, PPL for principal. Okay, I drew the principal axis with this dashed styling. Okay, and I'm very fortunate early in my school career, the principal of one of my schools, his name was Al Kadich. So his first name was Al. Okay, so you know there are 2 different ways to spell principal. The principle of superposition has an LE because that's a principle like a thought. But this is principle in the sense of number 1. And so again, Al Kadich, as the principal of the school, he was the #1 person, right? So it helps me to remember that, but I understand most people will have difficulty remembering if this is principal with AL or principal with LE. So yeah, the popular abbreviation here, PPL, for principal axes. We've drawn them like so, okay? Now let's talk about which one's the largest, which one's the smallest, okay? Well, you see our discussion here with the tennis racket, we can capitalize immediately. We know that this axis here will have the largest one. So this will be our largest, lambda, largest. Okay, and this will have the smallest, right? You see, if you look down this axis, the mass distribution is very close to the axis of rotation. So lambda, smallest. Okay, and this one here, there's only one option left, and that's intermediate. So this is lambda intermediate. Okay, and so you see, when an astronaut spins one of these handles about this intermediate axis, this is precisely the setting for this theorem, right? The so-called intermediate axis theorem. That principal axis is unstable. Of course, for all three of them, you can, in an ideal world, you can prepare the system to spin steadily about that axis. And the reason is, if you have omega exactly parallel to a principal axis, then the angular momentum will be constant, right? And that's, we're going to see that's the fundamental dynamical statement. Because there are no torques, right? We're assuming there are no torques on the system. The constancy of the angular momentum is the crucial thing. So if you have a principal axis, and if you prepare the system, meaning you throw the tennis racket into the air or you launch the dancing T-handle, if you prepare the system with an omega vector that is pointing along the principal axis, then the angular momentum vector will be a constant independent of time. Okay, that's exactly what we want, because we've assumed the torques are 0, so the angular momentum must be constant. So it's true that each of these three axes is an opportunity for a perfect ideal solution. Steady rotation about a principal axis is a solution, but stability is a different question. Just as you can balance a pendulum upside down, that's an equilibrium. It's not stable. The tiniest bump will grow exponentially. It turns out we're going to work out the dynamics. Okay, how does the axis of rotation evolve over time? And again, for the smallest, for the axis belonging to this smallest eigenvalue, it's stable. You give the system a little bump, it'll wobble, but nothing drastic will happen. Same is true here. If you get the thing spinning about this axis and give it a little bump, it will wobble, but it will continue to stay in this vicinity. But for this one here, the tiniest error, it could be a microradian or a nanoradian, very small error, it's going to grow exponentially. Okay, so there's a region of exponential growth in the small angle approximation, but what happens physically, it does a half twist. So we're going to see how the angular velocity vector goes and points over on the other side and then asymptotically approaches that for a while. So here you have this exponential decay. We'll set up the framework for that. Okay, so again, we've explained some major portions of the dancing T-handle discussion, right? We've explained that this axis is intermediate. Now, what happens if you have a dancing T-handle threaded into one of those sockets on the wall? And you do the cool thing, which is you remove it by giving it a spin. Well, you give it an initial angular velocity that's very close, but not quite equal. Maybe some astronaut has done it. It is conceivable. But typically, it's going to be very close with a slight error. Okay? So having said that, let's reward ourselves with one more look at the video. Here we go. Here we go. Okay, remember we said this axis is unstable. And you see the omega vector. Let's convince ourselves the omega vector is very close to this axis. So you see what's happening. It appears to be spinning about the axis, but then you have this growth of air and it does a half twist. Okay, wonderful stuff. Let's stop the share once again. All right, so let's understand that before we get into detailed calculations, let's understand that there's a tremendous amount of stuff you can do with conservation laws. And conserved quantities are important to us. All this, I shouldn't say semester, all this summer session, we've been talking about conserved quantities. So we can say two things. The kinetic energy is conserved and the angular momentum in the laboratory frame is conserved. So let's contemplate that. Okay, we're going to see that with this knowledge of the two conserved quantities, we can already answer a lot of questions here. We can resolve a lot of the question marks having to do with this behavior. Okay, so here we go with the kinetic energy. Okay, and if you like really cool formulas, I think you will enjoy this one. We're going to see that the kinetic energy of a rigid body is 1/2 omega dot L. Right? And in general, those are not parallel. Right? In general, omega is not parallel to L. Okay, this is a really cool result. We're going to write it in several different forms. Let's take a second to just appreciate there's some similarity. Let's recall the kinetic energy of a point particle. So I will make a parenthetical remark here, recall. For a point particle, right, the kinetic energy 1/2 mv squared and this is equal to 1/2 the velocity times the momentum, and I should say the speed, right? 1/2 the speed times the momentum. So far, so good. Now, for a point particle, the momentum vector is parallel to the velocity vector. So let's really emphasize here that v is the magnitude of the velocity vector, that p is the magnitude of the momentum vector. Okay, and so for this example, because these two vectors are parallel, it doesn't matter if you write v dot p or speed times magnitude of momentum vector, same thing, right? Okay, so you see the structure, velocity dotted into momentum. Now for a rigid body, we have angular velocity dotted into angular momentum. So you see there's a very nice parallel between these formulas. The remarkable difference is for a rigid object, these two vectors need not point in the same direction. The formula is still correct. It's not an approximation, correct formula. All right, let's prove this because it's a really nice formula. What you do is you have a sum of contributions. Okay, ultimately, at its very heart, for every particle, you have an r cross p. Right? So the proper way to say this is we're going to think of a rigid object, right, with this r cross p for the angular momentum, right? So L is a sum okay. So we're thinking of taking a rigid object, you chop it into little differential installments. Let's call those particles. And for each particle, you compute, oops, this is angular momentum vector. Forgot the vector arrow. Okay, so for each particle, you compute the contribution, that's going to be your position, crossed into the momentum. Okay, then we can write this, there are several ways to do this. Let's compute omega dot L. Okay, so we're summing over all the particles, and we have omega dotted into R alpha cross P alpha. Okay, so far so good. Now this is a vector triple product. It's a scalar vector triple product. That means you have three vectors. Here's this omega vector. We have a position vector, and we have a momentum vector. And this operation is a triple product. That's a dot product. That's a cross product. The result is a scalar. Okay, now you know you can cycle the factors. The most popular way to remember this is that you cycle the factors. The alternative is that you keep the symbols in the same order, but you just swap the two operations. You move the dot here, you move the cross there. Okay, that's fully equivalent. And of course, this result is available in the book. If you look in the back cover here, this upper one, this is the scalar triple product. And the emphasis here, again, is on the cyclic structure. You see it goes A, B, C. Then we push the A off to the left. It goes A, B, C. Again, the order cyclically is A, B, C. And then we cycle once more, A, B, C. So this presentation focuses on the cyclic worldview. In each of these three triple products, you have a dot and a cross. The dot is on the left, the cross is on the right, right? You see, that's certainly true. Now, I just want to emphasize what happens if you use the alternative formulation. Okay, so the alternative is you keep the three symbols in the same order and you swap the two operators. So we'll put the cross here and the dot here. And for clarity, we like to put parentheses. All right. Some people believe the parentheses are not necessary because they would argue A cross B gives you a vector, and the only sensible operation then is first you do the cross product, get a vector, and then do the dot product. But then there are others who would invoke certain, you remember we talked about tensor analysis last time. There are lots of funny operations you can do with tensors, and they can attribute a meaning to first doing the dot product and then the cross, and it can get rather weird. Let's just dispel any confusion, put the parentheses in. We've been very clear here. First you do this cross product, A cross B, that gives you a vector, then form the dot product with C, okay? Let's have a look over here. You see that equals this third form because the dot product is commutative. If you have a dot product, you can swap the two factors. If you have a cross product, you cannot swap the two factors. You get a minus sign if you do that. Okay, so in summary, we've shown that the alternative, which some people choose as their favorite way to remember this, the alternative is keep the three factors in the same sequence and just swap the two operations. Okay, so either way, you can remember it as cycling the three factors or this alternative form. Okay, wonderful stuff, absolutely wonderful stuff here. So let's use that. Okay, so what do you say we use the form where we swap the operations? Okay, so that means we keep the three vectors in the same order. And we're going to swap the operation. So we put the cross here and the dot there. And again, for clarity, voila. Okay. Okay, so now there's a useful relation. Omega cross the position, that's the velocity. So this is the velocity of that particle dotted into the momentum. Okay, and we just investigated that one. That's twice the kinetic energy of the particle. Okay, so this is equal to 2t. Right, this individual contribution was for particle alpha. That's twice the kinetic energy of particle alpha. And so when you add it up, you get twice the total kinetic energy. So this is the proof, and it's nice proof here. using our knowledge of vector triple products and using the useful relation. Okay, so I claim, most people are not really aware of this wonderful formula. So we're asking you to get out there and spread the word and tell people that for a rigid object, it's 1/2 omega dot L, and those vectors in general are not parallel. Wouldn't it be 2t alpha? Yeah, this right here, there's a question in the chat window. This thing here is 2t alpha, and then we sum on alpha to get the total kinetic energy. Let me make sure I got the whole question. That's right, absolutely, 2t alpha, and then you sum on alpha to get the total kinetic energy. Oops, let me raise the paper. Yeah, so this contribution is what we would call 2 times t alpha, the kinetic energy of particle number alpha, and then we're adding up all the contributions from all the particles to get the total kinetic energy. Okay, so what we can do here is we have 2 statements now. We have the constancy of the angular momentum and the constancy of the kinetic energy. Using these 2 things and using our knowledge of classical geometry, we can do some wonderful constructions. I'm going to save some time, again, just by displaying the result. And this will be in the notes that I publish. Okay. Again, I'm going to carefully fold this. The old philosophy, measure twice, cut once. That's how you say it. Measure twice, cut. In my case, measure twice, fold once. Okay. So here's the situation. We're going to ultimately justify this picture here. Okay. This is a picture, and in the lecture notes, I will publish a very nice diagram created by some of our friends across the street, and I'm referring to Evans Hall, right? All the famous mathematicians in there. They actually love the problem of the free rigid body. It's one thing that helps justify their existence when they can say, hey, people over in the physics building care about this stuff, and they have these very advanced, sophisticated methods. This stuff is a special example of some more general things they like to do. So yeah, we'll talk about a separatrix here, etc. What is going on here is we have a very general notion here, L1, L2, and L3. These are the components of the angular momentum relative to the principal axes. So let's take a second to write down what that means. Okay. So the notation goes like this. You remember we have typically a laboratory frame, and we can describe that like so. Okay. And this is why we set up a very general framework for talking about how tensors transform, right? We have an inertial frame. The lab frame is the inertial frame. Okay, so lab frame, inertial frame, and this is a familiar picture to us. We have these 3 axes, XYZ axes. They are mutually orthogonal, et cetera, and so forth. It's a right-handed system. So that's our lab frame. Now, think of that dancing T-handle. If you were a little micro robot sitting there, and they have these little robotic claws, they can really hang on with those robotic claws. Hanging on to the dancing T-handle, that's not an inertial frame. You're tumbling and getting motion sick. So the other frame is going to be our frame like so, the non-inertial frame. Okay, and the unit vectors here, we like to have these, we talked about them before. At that time, we were talking about a potato, perfectly good example. You have a rigid object. You can easily stick 3 toothpicks into the potato, and that's a useful picture to have in mind. Here we have the E hat 1, the unit vectors are E hat 1, E hat 2, E hat 3. So here's the E hat 2. And of course, this one. Okay. So this is again our convention. We have stuck 3 toothpicks into the potato, so to speak, the center of mass right there. And they are unit vectors, so we put the hat. This is E hat 1, E hat 2, E hat 3. All right. The crucial thing, and this often causes confusion, we're going to talk about the angular momentum vector relative to the body frame. So this lab frame, inertial frame, in this business, it's called the space frame. Okay, that's just a couple hundred years of history. Everyone uses this term, so just remember the space frame. That's what we're going to use it now. Use now for this frame. We'll use this term space frame, and the red one is called. Remember, we would have called it the non-inertial frame, the red frame, and I should use red ink for this, right? So non-inertial frame. Okay. In chapter 9, we would have loved this terminology: inertial frame, non-inertial frame. In the studies of rigid body motion, this one is called the body frame because it moves along with the rigid body. Remember, the subject is called rigid body motion. So this is called the body frame. Okay, so I have indicated that our preferred notation here, space frame, body frame. Okay, we got a situation here. My wife says nowadays animals, pets are part of Zoom meetings, and we have to deal with that. This one has arthritis. She needs help getting, and just burn. All right, sorry about that. But you wouldn't want a cat to jump off the bed with arthritis. Come on, that's going to hurt like crazy. Okay, so the crucial thing now is we're going to talk about the angular momentum relative to the body frame. Okay, so here's the angular momentum, Lx, Ly, Lz. Okay, that means you have an angular momentum vector, and you you read off the components relative to these black axes, the x-axis, y-axis, z-axis. So in the body frame, we're going to talk about L1, L2, L3. Okay, and the fundamental paradox that people often ask is, well, in the body frame, the body is motionless, so the angular momentum would be 0. Okay, it's true that in the body frame, the body is motionless. But what we're talking about here is the angular momentum. So this is computed in the lab frame. So computed in the space frame. Okay. So you can think of it as a 2-step process. We compute the angular momentum in the space frame, and then we transform. So then transformed. Right. So of course, in the body frame, if you attach a little video camera to the rigid object, be it a tennis racket or a T-handle or a potato, if you attach a little camera to it, then and you watch the video feed from that camera, then obviously the body is motionless. So that's not what we're talking about here with the angular momentum relative to the body frame. We're talking about computing in the space frame. So you can imagine the following process. So scientists in the space frame, they compute the angular momentum, and then they get an assistant to hold a pointer in the direction of the angular momentum. And that's going to be a constant here for the free rigid body. Angular momentum doesn't change. And then you have a video camera attached to the rigid object, and it's viewing this vector, which is motionless in the laboratory frame. Okay, so in that sense, we have an angular momentum vector that's moving around in the body frame. Okay, that's the crucial thing. Now notice the two frames are related by a rotation. So both people agree. So if you have observers in these two different frames, they both agree on the magnitude. So another way to say that is that Lx squared plus Ly squared plus Lz squared, right? Remember our nice discussion on tensors yesterday? That's a rank 0 tensor. That's the dot product of the angular momentum with itself. This is equal to okay. And so again, this is the rotational invariance, right? The rotational invariance of the dot product. The length of the angular momentum vector is the same in the black frame or the red frame. Now in the space frame, these three things individually are constant, right? Because in the space frame, for a free rigid object, an object with no torques on it, the angular momentum vector is a constant vector. So these are all constant. Okay. In the body frame, these individual things are not constant, but the grand total, the sum of the squares, is a constant. Okay. So with that in mind, you see we have two things to talk about. We know the kinetic energy is constant, and we know the length of the angular momentum vector is a constant. So this is very powerful that we have these two conserved quantities. Again, constancy of kinetic energy and constancy of the length of the angular momentum vector. Remember, the length of the velocity vector is called the speed. We don't really have a special name for the length of the angular momentum vector. Okay, so now let's just review these diagrams. So we'll take those two statements, right? The constancy of the kinetic energy, right? In fact, I think I'll just, to save some time, we're gonna just look at these notes. We proved this earlier today, right? The kinetic energy, omega dot L. Now, the angular momentum is the matrix I times omega, and that's a matrix product, okay? And that's then the dot product, okay? So you write this out in principal axes. We have one expression for the kinetic energy like so, and then you can rewrite this so that your kinetic energy, it has a structure of, it's down here at the bottom. The kinetic energy is, there's a 1/2 as always, and you have L1 squared over lambda 1 plus L2 squared over lambda 2 plus L3 squared over lambda 3. Okay, so let's just remember that we have the constancy of this kinetic energy. So T, we'll copy that one over. It's definitely a keeper. So that's a 1/2. The L1 squared over lambda 1. We got the L2 squared over lambda 2. L3 squared over lambda 3. Okay, and that's a constant. Okay, so now behold what happens. We have this, if you plot this in a three-dimensional space, this is an ellipsoid. Right? It's kind of like a sphere, but you stretch it different amounts along different coordinate axes. That's an ellipsoid. So we have two things. We have a sphere. This truly is a sphere. If you draw a space, a diagram with three axes, L1, L2, L3, This is saying we have a sphere, okay? And this is saying we have an ellipsoid. So we're talking about the intersection between an ellipsoid and a sphere. And this is great. It's time for some classic geometry. We need to visualize the intersection between an ellipsoid and a sphere. So that's what we're going to do here in these pictures. We're going to visualize the intersection between an ellipsoid and a sphere. So first, let's think about the ellipsoid. You can kind of think of a surfboard, or sometimes you see lifeguards when they go to rescue somebody, they have this red flotation device, which is somewhat shaped like this. It's kind of, this thing is like a surfboard, except a real surfboard has some rocker to it, meaning it's like a rocker on a rocking chair. It's not perfectly flat. This would not do so well if it were like this. Okay, the point is, this is a picture of an ellipsoid. If you slice it like so, you see this dotted line here. That's an ellipse. If you slice it in the L1, L3 plane, that gives you this dotted line. That's an ellipse. And of course, you could slice this in the L1, L2 plane. I didn't show that. Actually, I did show that. Sorry. That's this one here. Oh, I did show that. That's the L1, L2. Wait a minute. No. This one is definitely the L1, L3. You see they intersect down there. I did not draw the other one, the L2, L1. Okay. The point is, these are different ways to help us visualize this is an ellipsoid. Okay. And we need to think about the intersection of an ellipsoid and a sphere. Because when you launch a rigid object, be it a tennis racket or a T-handle or anything else, you define the initial conditions. When you let go, you have defined initial conditions that determine the subsequent motion. In particular, you've defined the kinetic energy about the center of mass and the angular momentum vector about the center of mass. Okay. And so in other words, you've chosen a couple of things here. Now in this picture, in red pencil, I drew a sphere. And you chose the radius of that. When you launched the object, you chose the radius of the sphere, right? It's the radius of the sphere is the length of the angular momentum vector. Okay. And now let's talk about the intersection. So what's the intersection between a sphere and an ellipsoid? Well, remember this in black here is kind of that surfboard shaped thing. And we want to think about the intersection with a spherical shell. So in the pronounced red pencil shading, I drew that here. This is kind of like an ellipse, but it's not really an ellipse because it's not planar. Remember, this is on the surface of a sphere. It's on the surface of this big sphere. But you can kind of think of that as an elliptical thing. Okay, so now there are a family of different intersections, and there's one very special one, the so-called separatrix, right? So the separatrix is shown here. You see how we have this intersection of two kind of straight-looking lines. But let's talk about the two generic cases. If you have a small sphere, such as this one here, this picture shows a sphere in the light pencil shading, and then in heavy red pencil shading, the intersection between that sphere and the same ellipsoid, which was the surfboard. And in this case, we have these two kind of circular looking things. Okay, so for the small sphere like so, we have these two circular intersections. For a larger sphere, we have these two intersections. They're nearly elliptical. Okay, and of course, these are nearly circle. They're not perfect circles. And in between, we have a transition, right? So for the very large spheres, you see there's a family of these pronounced red shading. There's a family of those. They become larger or smaller as you change the radius of the sphere. Okay. When the sphere gets really large, they shrink down to just a single point. And that's a very special point. Of course, that's the eigenvector. Now, when this gets smaller, eventually that shrinks down to a single point. And there's a transition. And that very special transition is this separatrix. And now you can see in this picture here at the bottom, right? So you can see there's a whole family of intersections. The separatrix, again, that's a general term. When you solve differential equations, a separatrix is a boundary between regions. And the solutions to the equation of motion, the solutions to the differential equations, they exhibit different behavior in the different regions. So here, in this region, you see all these curves, they circulate about this L1 axis. So we haven't talked about the dynamics yet, right? There are equations of motion that we're going to work out to explain how the angular momentum vector moves around in this space, the L1, L2, L3 space. It's going to move around. Remember, we talked about the fact that it's not constant in the body frame. It is constant in the space frame. So when we work out those equations of motion, these will be called the Euler equations. Once again, same researcher, Euler. We'll be able to solve for how quickly or how slowly the L vector moves along these curves. But before doing that, we want to observe we can make some very powerful statements just using the existence of these two conserved quantities, the conservation of kinetic energy and the conservation of angular momentum, which in the body frame is this statement that the length of the angular momentum vector is a constant. Okay, so again, when you throw a rigid object into the air, you've defined initial conditions that define its subsequent motion. In particular, you chose the radius of this sphere, okay? And the initial kinetic energy, you can go through the arithmetic. Capital T figures into these intercepts. You just write down the equation for the ellipsoid. You can work out these intercepts, okay? Now the lambda values are constant. They are attributes. So if you have the paddle, here's a paddle. This thing has 3 principal moments of inertia. And I think they should stamp them on here, right? But they didn't. So a fun project would be to determine the 3 eigenvalues and write them on here so people know. Anyways, the point is we want to emphasize those 3 lambda values are properties of the object. They are not determined by your initial launch of the object. Okay, they're attributes of the object itself, just like the total mass of the object is an attribute of the object. Okay, so for this discussion, you should think of lambda 1, lambda 2, and lambda 3 as simply constants. You can't do anything to change those, right? We're assuming those are the rules of the game. Obviously, you could saw off a portion of the paddle. That would change these numbers. But when you throw the thing into the air, you choose a value for capital T, the initial kinetic energy, and you choose a value for the length of the angular momentum vector. So then you can draw this picture. And so in summary, you have chosen one of these red curves in this picture. And the special cases, the very special cases are these dots. This one would be if you have achieved what we can only dream of, which is throwing the thing into the air, exactly spinning about a principal axis. In the language of this picture, that means you would have chosen one of these dots here, this dot, and this dot. Those are all cases where the angular momentum in the body frame is also a constant. It's constant in the space frame and it's a constant in the body frame. So these 3 dots, we see the dot here, a dot here, and a dot there. Those are the case of steady rotation about a principal axis. Now you see what happens if you're near this number 3 axis, but not quite at that dot. Well, the evolution of the system will be confined to this curve. Our argument right now with the energy analysis, we know it's confined to this curve. We don't know exactly how quickly or slowly it's moving around there, or if it explores the whole curve, but we know it's confined to that curve. Later, when we work out the equations of motion, we'll be able to write down how quickly it moves around this curve. Okay. And the same is true for the number 1 axis. It's going to move around this little curve for a typical launch that's pretty close to the number 1 axis. But the intermediate axis, the number 2 axis, is the intermediate axis. And here, if you prepare the system near this fixed point, it's going to exhibit exponential growth. And that's, again, in the sense of the small angle approximation. Just as a pendulum, if you prepare the system near the inverted equilibrium, or it's pointing nearly straight up, then that tiny error is going to grow exponentially. That's true as long as we have the small angle approximation that we're looking at small angles. We can solve the equation very nicely and get this exponential growth. All right. So yeah, we're going to see there are stable and unstable manifolds. And you remember at the beginning of the course, we looked at some slides by Kathleen Howell, professor at Purdue, and we talked about stable and unstable manifolds in higher dimensional contexts. Well, here's a manifold In this case, we have a two-dimensional space, right? This surface of the sphere is a two-dimensional space, and we have two manifolds. We're going to see that at this special location here, this critical point, there's a stable manifold where the flow moves towards the fixed point, and there's an unstable manifold where it moves away. So we're starting to see relationships to these kind of fascinating concepts. Okay, so we've reached the 2 o'clock hour. I'm going to stop the recording and I'll stay here for questions.